Hello everyone. We continue our lectures with series solutions near an ordinary point for differential equations. This subject is divided into two parts, and we will discuss the first part in this video. In this lecture, we consider the second order homogeneous equation with non-constant coefficients. And here, I label this equation by a triangle to refer to it in the future. We suppose that the coefficient functions p, q, and r are polynomials and they have no common factors. If so, we can divide them out. And as a second assumption, we let the solutions be in the neighborhood of a point x0. That is, the solutions are given in an interval which contains x0. Now, let me give a definition. A point x0 such that p of x0 is not equal to 0 is called an ordinary point. That is, a point which makes the coefficient of the second derivative non-zero is called an ordinary point. Using the fact that p is continuous at x0, we can divide a triangle equation by p and obtain an equivalent second-order differential equation with different coefficient functions, say small p and small q. Due to the existence and uniqueness theorem, there is a unique solution of the differential equation triangle, and this solution is given in an interval which contains x0, and it also satisfies the initial conditions given at x0. However, if p of x0 is equal to 0, then the existence uniqueness theorem doesn't apply, and such points are called singular points. We will consider such situations in the future. Let's turn back to our main subject. We are looking for solutions to the triangle equation using power series. To that end, we will assume a power series representation for y about the point x0 and try to solve for the coefficient a(n) in the series. We assume that the series converges in the interval absolute x minus x0 less than rho for some positive rho. And you may recall from calculus that rho is called the radius of convergence. Let's see an example. Find the series solution for the differential equation y double prime plus y equals 0. As a remark, sine of x and cosine of x form a fundamental set of solutions to this differential equation. One can obtain this result using the characteristic equation. Our purpose is to find a series solution to this differential equation. But before, we need to classify the set of ordinary points. Since p of x is equal to 1 for all x, every point is an ordinary point for this differential equation. In particular, 0 is an ordinary point, and we will choose x0 be equal to 0 for simplicity. We assume a solution y given as a power series, which is the sum from 0 to infinity of an times x to the n. Then we differentiate the series for y term by term and obtain power series representations for y prime and y double prime. Here observe that the series for y prime ranges from 1 to infinity, whereas the series for y double prime ranges from 2 to infinity. After finding the series representation for y double prime, we substitute this together with y into the differential equation and obtain such an equation. The first sum ranges from 2 to infinity with the power function x to the n minus 2, and the second sum ranges from 0 to infinity with the power function x to the n. In order to have the same generic term x to the n, we rearrange the index of the first series and then collect all the terms under one infinite series given here. And as we observe, for this equation to be satisfied for all x, the coefficient of each power of x must be 0. Then we end up with the following reconciliation. And as we observe, if we start with a0, we can derive all the even-numbered coefficients, like a2, a4, a6, and so on. And if we start with a1, we can derive all the odd-numbered coefficients, like a3, a5, and so on. So let's start with a0. Then a2 is minus a0 over 2 factorial, a4 is a0 over 4 factorial. Be careful, we don't have here a minus sign for a4. And a6 is minus a0 over 6 factorial, and again we have a minus sign. Then we can derive the formula for the even numbered coefficients. Say a2k equals the minus 1 to the k over 2k factorial times a0. And one can prove this formula using mathematical induction. And similarly, by starting with a1, we can get a3 equals minus a1 over 3 factorial, a5 equals a1 over 5 factorial, and again, there is no minus sign in front of this expression, and a7 is equal minus a1 over 7 factorial, and so on. Therefore, we end up with the odd numbered coefficients. Say a 2k plus 1 equals minus 1 to the k over 2k plus 1 factorial times a1. And as before, one can prove this formula using mathematical induction. After finding out the even indices and odd indices, we are ready to substitute these coefficients into the series expansion of y, which is a0 plus a1 times x plus a2 times x squared. But since a2 is equal minus a0 over 2 factorial, we substitute it over here. And the remaining terms can also be given in terms of a0 and a1. Therefore, if we collect the terms which involves a0 and the terms which involves a1, then we end up with the expression y equals a0 times a sum which involves even indices plus a1 times a term which involves odd indices. Now call the first series as y1 of x and the second series as y2 of x. And one can prove that both series converge for all x, and this can be done by using the ratio test. However, it's well known that y1 of x is the Taylor series for cosine of x about x0, and y2 of x is nothing but the Taylor series for sine of x about x0. All in all, the general solution of y double prime plus y equals 0 is given by the linear combination of cosine of x and sine of x as expected. And that's the end of the lecture. See you on the next video.